Okay. Do you hear me?
Yes.
Do you see the screen?
Yes, miss.
Okay. So I think this is the part where we ended. The linear velocity of the gas converted to the gas mass velocity using the density. So as I mentioned, this is already the gas mass velocity at flooding. So we intend to design our column at 50% of this flooding condition. So we, wait gosh. So we will have to multiply it by 50%, and that should give us a value of 0.2435 pound mass. So take note of the unit, pound mass per second per feet squared. So it's gas mass velocity per unit area actually when you look at the set of units. Now, since we determined the gas mass velocity as 50% of that of the flooded condition, we do the same thing for the GL. So since we have the ratio of 2.0 for GL to GG as stated here in that problem, we will have to multiply the value that we got here for G sub G, which is 0.2435 by 2.0. And that should give us a 0.4870 pound mass per second feet squared for the gas mass, no, for the liquid mass velocity, because L is for the liquid. Liquid mass velocity at 50% of the flooding condition. So to calculate for the tower pressure drop at 50% of the flooding, the GG and the GL, you will have to use this as the new GG and GL at 50% flooding condition, and the new capacity parameter, of course, of 50% for 1.7. If you recall, the 1.7 that we got here is based on the flooded condition. So we are to multiply it at 50% of the flooding condition, and that should be 0.85. This particular 0.85 together with the value of 0.0683 for the flow parameter. So I would like to emphasize this class that your flow parameter is the same even if you change already the capacity parameter to 50% of its value. If I may ask, why do you think is the flow parameter the same even though this one was already decreased by half? Why do you think the same? Your flow parameter is the same, whereas your capacity parameter was multiplied to 0.5 because we want to design our column at 50% flooding. Anyone? Okay, so the flow parameter will not be affected even though we are now considering a condition of 50% of the flooded condition. It's because your GL-GG ratio is still the same. It's still 2.0 even though the GL and the GG themselves were decreased by half. So the ratio is still 2.0. So that's the reason why you still have the flow parameter as the original flow parameter with the 1.7 multiplied by 0.5 so that we will know the new pressure drop at 50% of flooding conditions. So using the 0.70, 0.85 for 50% of 1.7 and the flow parameter, we will get a new pressure drop of 0.18 inch water per foot of packing material. What is this? This would be the pressure drop at 50% flooding condition. Whereas the original one that you determine is the pressure drop at flooded condition. So when it's 50% not flooded, far from being flooded, this is only the pressure drop, 0.18. Look at it. It's only 0.18, whereas when it's flooded, it's 1.925. So very high. The difference between the two is very high because this one, your column is not flooded, but it is here, it's flooded. So how do we determine, next is how do we determine the cross-sectional area? So this one requires the knowledge of your thermodynamics before. But before we can do that, since our mass flow rate, the feed flow rate, that is the mass flow rate of the feed is in pound mass per hour, we will convert this to pound mass per second. And there's a need for us to divide by 3,600. Why convert from pound mass per hour to pound mass per second? Why? Why is there a need for us to convert this one, the 1,440, to a value lesser than that by dividing it by 3,600? Anyone? Okay, it's primarily because your units here for time are in seconds. So you don't have units for time here, which is hours. So this is per second. Your linear velocity is even in seconds. So your mass velocity, which is per hour, should be converted to seconds. This is just a case of finding the cross-sectional area using dimensional analysis. Why? You are given here the feed rate, the mass feed rate per second, and you are to divide it by the gas mass velocity at 50% flooding condition. So that would be the 0.2435. So if you divide it by the unit pound mass per second per square feet, the remaining unit is already a unit for area, which is in square feet. So that's just dimensional analysis. You make use of the feed rate, you divide it by the gas mass velocity at 50% flooding condition. When you know already the cross-sectional area, the diameter will just follow. So the diameter from the cross-sectional area is 1.446 feet. So you have the equivalent there in meters. So we determined the pressure drop at 50% flooding. We determined already the tower diameter. So we have designed our column. However, what should be the value of the gas and liquid flows at this current condition, which is 50% flooding? So we will continue. Now, the outlet water will carry the absorbed ammonia if we will assume that all the ammonia in the ammonia air mixture will be recovered by water. So the problem actually, class, is silent about recovery. There's no mention here of how much of the ammonia that entered will be recovered by the solvent. So we will just assume, just for illustration purposes on how we will determine the gas and liquid flows, that the recovery is 100%. So we determine this time the amount of ammonia that entered. So this is the part where the 0.01783 that you solve here at the beginning, this one, the weight fraction of ammonia of 0.01783, you make use of it now. So if you did not determine this initially anyway, when you go to the last part, you will still determine it. Why? Because the problem gives you the flow rate in mass. And you have everything here in moles. So there has to be a conversion, or you have to determine the actual mass of ammonia that entered by using the weight fraction of ammonia. The conversion that is of the 3 mole percent to mass fraction. And that's done here. That's the procedure here. So now you made use of this data and you have this ammonia that entered. So naturally, even if you're not a chemical engineer, common sense will dictate that all of this ammonia will go with the water. So where is it? Okay, not yet. Since the liquid flow rate is twice or 2 times the gas flow rate, the total liquid flow rate is, so this is your total liquid flow rate. You may wonder why, where is this 2 times the gas flow rate? That's this one, sorry. It came from here. The process design specifies a liquid to gas mass flow rate ratio of 2:1. So now we know that our liquid then must be twice of the original amount of feed that was processed. Hence, the flow rate of the pure inlet water is 2,280 minus 25.68. and that would be 2,858.3 pound mass per second. Now, this is already on the connotation that this 2,280 of the liquid carried with it the 25.68 pounds of ammonia that was absorbed. So the original amount of liquid that entered the column is actually 2,858.3 only. So take note, class, ha? The ratio that was mentioned here, the GL over GG, is the ratio of the gas that entered to the liquid that left the column. Why? Because this is to the gas that entered to the liquid that entered the column. The gas that entered is 1,440. The liquid that entered the column should be 25.68, less than twice of this one because it carried already the ammonia. So we took it from there, and this is now the flow rate of the pure inlet water that went into your column. Now, as to the rest of letter B, it's the same as that of letter A. The same as that of letter A because the only difference here is just the use of the packing material, which is the Melia packs. The rest will just be the same. In terms of procedure, the entire procedure that was outlined will be the same. Do you have any questions so far? I will not discuss letter B. You can practice this during your spare time using Melia packs. At least you have already the values here to check whether you are doing the right thing. Question? No question. Then we will proceed. We determined so far the size of the column if the column is a packed column. That is why we use the identity of the packing material that was used. If the column is a tray column, we'll be using, of course, a different parametric set of equation and curve. So if it's a tray column, this is how you determine the column diameter and pressure drop. So you obtain the case of V. I will show to you the figure later. You determine the entrainment velocity based on this equation. This is the entrainment velocity, meaning the velocity of the gas in which it will carry with it the liquid. Supposed to be the gas is going to leave the column with no liquid entrained. But in this case, due to the fact that your column is flooded, it will carry with it already, or it will entrain with it liquid. So this is the maximum velocity. So you have the kV taken from the figure. This is the interfacial tension. Most often value used is 20 dyne per centimeter for organic liquids. For water, it's 72. But you will notice in a problem later that is used here that even lesser than the value of 72 was used for water. The value used was 70. You can do that. Now, the typical value, and that is the maximum value for this linear velocity so that the column will not be overflooded, because I think at 3 meters per second, it's about to be flooded. It's 3 meters per second. And then you choose diameter so that gas velocity is just about 70% of what you computed here. So meaning, you solve for that diameter using a velocity value of 70% of the computed maximum velocity. The pressure drop usually much larger than in packed columns because of the pressure drop for gas to pass through the liquid on trays. So it's a given for tray columns class that your pressure drop will be greater than that in your packed column. And the formula for determining the pressure drop in tray columns is the delta P dry plus rho L. Rho L is the density of the liquid times the G, which is 9.8 times the H. The delta P is the pressure drop through holes of the tray. That's the pressure drop through the holes of the tray. And H, take note, is the sum of the liquid levels on all trays. And this is about 10% of the column height. So the sum of liquid levels on all trays, which is about 10% of column height. So the problem will make mention of this, otherwise we won't be able to determine delta P for our tray columns. So we have this from John Couples. Again, look for its equivalent in your handbook. You have in the abscissa here, L over V times rho V over rho L raised to 0.5, and that's the square root of the ratio of the two. You need the tray spacing, so the problem has to give you the tray spacing. So using the value computed for the abscissa, you have to go up, project until you are on the right curve for the tray spacing stipulated in the problem. Then read on the left the KV that you will use here, so that you will have the velocity maximum. Then use only 70% of that velocity maximum, so that you'll be having the area of your column. Okay, this is a sample problem that will illustrate the tray diameter of a valve tray absorption tower. This is again taken from John Couples. This time we are to recover ethyl alcohol from air, and we are using pure water as a solvent. The operating temperature and pressure of the column is stated. Your gas has 2% mole by mole ethyl alcohol in water, and 95% of the alcohol is recovered in the outlet water. So 95% of the 2% will be recovered by the solvent water. The inlet pure aqueous flow is 186 kilogram mole per hour. So pure, it does not have any ethyl alcohol. And the inlet gas flow is 211.7 kilomole per hour. Again, we are to design our column by determining its diameter. Here, the tray spacing is given to be 2 feet. And use a factor of 0.95 for possible foaming. So let's see on how we're going to make use of this information for possible foaming in designing our valve tray absorption tower. So we will determine again the molecular weight. Again, I guess this is a requirement for all gas absorption problem, especially if you're given flow rates and mass, and then the concentrations are in mole. So you need the average molecular weight of your gas together with the contaminant. In this case, our gas is air, your contaminant is ethyl alcohol. So since it is 98% only air, so notice that the air here is 29, it's not 28.97. It's okay. And you have 2% alcohol. Ethyl alcohol, molecular weight used is 46.1. This is the average molecular weight of your alcohol-air mixture, okay, that entered the column. Then also, we determine the density of the vapor. So again, PM over RT. So you may use the appropriate universal gas constant in order to get the density. So in this case, the density is 1.280 kilogram per cubic meter. The mass flow rate of the gas is 211.7. Take note, the unit is mass. 211.7 kilogram mole per hour. The unit that is required is mass. So you need to have the molecular weight, the average molecular weight of your mixture of gas and ethyl alcohol to convert the mole unit of the gas to mass. So now it's converted to mass. So the moles of ethyl alcohol, based on this amount of gas that entered in terms of mass, is 2% of that. 2% of that times 0.95, because we have 95% recovery. So moles of ethyl alcohol absorbed is 4.02 moles. So the outlet aqueous flow rate is L, which is 186. That's the pure 186 kilogram mole water. And the recovered, the 95% of the 2% recovered. So you have a total now of the liquid leaving the column as 190.02 kilomole per hour. Now, since you have converted your gas and mass flow rate, we will do so with the liquid. So your liquid is 186.0. This is for the water. So you multiply it with the molecular weight of water to convert it to mass of water. And then you have here the moles of ethyl alcohol, multiply it by the molecular weight of the alcohol to give you the mass flow rate of the liquid leaving the column, carrying with it the recovered ethyl alcohol. So the gas and the liquid now were converted to mass. Gas entering in mass, liquid leaving in mass. So the outlet water density, assuming that it's a very dilute solution at 30 degrees Celsius from the appendix, is given to be this one. So you get the density of water at 30 degrees Celsius because it's the operating temperature of your column. Sorry. And that would give you a density of 995 kilogram per cubic meter. Why get all this? The V, the L, and the density, you need it here in the abscissa. Need it in the abscissa here for you to get the KV. So we go back to our problem. The L, the living water, divided by the gas that entered, times the density of the gas computed divided by the density of the liquid taken from the appropriate property table. And you have the value of the abscissa of 0.02040. So if you use this value together with the 20-inch tray spacing, that value, that is 24.0204, somewhere here, you go up here, here, and read here. So the KV, let's see, the value of the KV is 0.385, more or less on this particular range of value. If you substitute it on the equation, direta class, 385, wala ta kalabot sa 4.0204, arilan di siya na, dire siya dampe. So this KV is actually that KV here. You will determine this one. So that's what we're going to determine next here. So maximum velocity using the formula will be 13.78 feet per second. This is maximum velocity when your column is in the verge of flooding. So multiplying the above by 0.91 to account for downspout area and 0.95 for foaming and 0.80 for 80% flooding. So take note, if in the absorption column, and we are going to design a packed absorption column, as suggested in the problem, it's only 50% of the flooding condition that we are using. Now, in the case of the tray column, you're using 50% of flooding. So you multiply 0.91, 0.95, and 0.8. If you don't have this foaming thing mentioned in the problem, then you will only have to account for 0.91 for the downspout area and 80% of flooding condition to get the designed linear velocity so that your column will be not flooded. Ini siya flooded na siya, on the verge of flooding. This one is, it's not flooded because you have multiplied it by 80%. You have accounted for foaming and you have accounted for downspout. Now again, using your thermodynamics to get your cross-sectional area given the linear velocity, you will be needing the volumetric flow rate. So you see the volumetric flow rate here, 6211. Where is that? The 6211 is for the mass velocity. You just converted it for the time in seconds. So you divide it by 3,600. Now, you want to get rid of the mass unit, so you have to divide it by the density. The density of the what? The density of the gas. That's the density that you have solved there. Okay, if you see my cursor, you will have now a unit in cubic meter per second. The cancelled hour, kilogram, kilogram, cubic meter per second. So to give you a unit in area, that should be divided by the linear velocity that you got here. And that would give you this area. And the rest is your geometry. How do you find the diameter given the area? So this would be our diameter. So this would be how we design our tray column in terms of the diameter. Now, the process of determining the height will, again, I think require a separate lecture. So I will continue with the lecture on the height portion of this on Thursday. I will stop the recording here for now, but I will again post a recording for the height computation, because in itself, it has several procedures that you may opt to memorize, but if not, just select one particular procedure that you are comfortable with. Because basing on the time, it will not really fit on the time remaining, which is just around 14 minutes in terms of determining the column height. But after this, we are really done with the topic on gas absorption and stripping. And that is done with the principles of gas absorption and stripping, the material balance, and then the design of the equipment that will carry out such particular processes. So I will stop recording.